Welcome to ONTOFORCE monthly webinar. My name is Marit Overbeke and I will moderate today's session. And before I introduce you to our speaker, let me quickly explain you about our company ONTOFORCE. ONTOFORCE delivers big data fabrics, allowing business users and data scientists to ingest, view, and analyze trusted data sources faster, gaining new insights for innovation and accelerate go-to-market and ultimately squeeze out time. It is our mission to build the best-in-class linked data platform to easily find insights in a continuous growing amount of data. Today's speaker is Philippe Patin. Philippe is the scientific lead at ONTOFORCE and will explain today's use case. Afterwards, you'll have the option to ask questions by raising your virtual hand via the Zoom application or via the chat function. Philippe, the floor is yours.
Thank you, Marit, for the introduction. So good afternoon or good morning from my side too. So I would like to address a little bit more in detail today about what we do in order to help you with if you would like to identify or validate potential targets in respect to drug development. So what is the agenda of today? I will very briefly touch on what is the topic of today, target identification and validation, a little bit in a broader perspective, sketching this, giving you a brief introduction to the public version of DISQOVER, showing you the setting of how we operate our platform and how we deal with public data. Then I will very briefly also touch on the data sources we use for this demonstration. So I try to mimic like a real world situation in a very simplistic way. For people who are inside the domain, it will be very easy to understand, but it's more about the principle of how we link data together, how you can set up a data workflow instead of really going for true scientific results. It's more about the principle here. And then in the end, I will give you like a demonstration of a local setup of DISQOVER, like a private setup of DISQOVER, where we integrated a limited number of sources which could mimic a target identification or validation workflow. And then in the end, we have some questions to answer. So if we go a little bit to a more high-level overview of this topic of today, it's all about time squeezing and optimizing the time to market in drug development. In the early stages, if you are still in discovery and you try to identify your targets or try to validate your targets, it's all about being as flexible as possible, combined with a good workflow that you don't lose time in making selections, failing early if necessary, but also bringing the right information together so that you can make well-informed decisions. For people who are inside the domain, this is very common sense, but it's all about how to get things together, also in bigger teams, how to get your information nicely combined. So if you think about this, what are the different possibilities you have available? There is a lot of data in the public space, and it's really immense. The problem is the data is in different formats. It's very difficult sometimes to bring this together. It's not easy just to use it for the purpose of your validation or filtering and selection. The same thing applies also to internal data. If you are in an organization, you're already dealing with data, you have produced a number of data sets that you would like to eventually use again over and over. This is not trivial too. And also, we have a constant evolution in the availability of certain techniques. There is a constant way of inventing new technologies which are producing different types of outputs and which also sometimes make it difficult to combine. So on the right side, we show like a funnel. It's just a figure I took from a publication with a certain target identification and validation strategy. You can see this as a number of sequences of steps where you would like to drill down from a larger set of potential targets to a more narrow set, better filtered, better selected set. What are the needs? The needs are definitely that you would like to bring together different data sources, internal and public data sources. You would like to streamline the whole process, that it runs as efficient as possible. You would like to, when it's successful, reuse certain processes or strategies. And ideally, you would like to integrate the different tools you are using into an ecosystem so that you have a natural flow of your data towards information, towards decision making. So very briefly introducing Discover. So if you go to www.discover.com, you will see our platform in action. It's an open access version of our platform. I will briefly go to that. So I will leave the application here for a while, the presentation for a while, and go to this screen. So what you get here is discover.com. This is the default environment where we operate. You can have access here to a lot of data sources. Some of them are very relevant to what we are looking at today. And what you typically see here is a default search bar. So you can enter here different values, different entries. You can click on search and you will get results. How does it work with the results? You see here these different circles. These circles represent what we call data types. So that means that everything you are searching for will be located or will be a part or a result will be inside one of these data sources. So if I'm looking for a certain gene, TP53 for example, I see immediately a highlight where I can see, okay, how many times do I find TP53 in all these different data types? If you hover over gene, you will see two values, 206 and more than 3,400. That means the first number, and it's also with a green background, that we have 206 identical matches with the concept TP53. That means that there are more than 200 genes in different species which have the name, the synonym term, the alternative name, the symbol, etc. of that specific entry I made, so P53. But there are also more than 3,000 genes where TP53 is mentioned somewhere in the connotation, in the annotations, in the links. And then you have other values like chemical. It seems to be that TP53 is positioned 2 times as a chemical. But then you see other hits where you just find an occurrence, a text match with TP53. What is now possible is that I'm, like I was mentioning, looking for a certain gene, and you see here the different genes popping up. I'm interested in TP53 from Homo sapiens, so I can select this and can expand my search. So I'm expanding my search, combining different synonym terms, and so I have a broader look for information. So I had first like 30,000. I can go back to that and show you that first. 32,000 results here. If I'm expanding my search and I'm taking also P53, for example, I can expand my search and get more than 100,000 publications. So what it means here is that you immediately make a selection. What is, you may make a disambiguation, what is the data type you're mostly interested in? So you can select here publication, you go to publications, and you see more than 100,000 publications here, all showing together the results, and then you can make a selection. A possible strategy could be that you select only publications very recently, so from the last 2 years, and you say, okay, I would like to see only publications from a specific journal. That's a possibility. Or you can add another filter criterion by adding, for example, an additional filter here. So if I'm clicking here on the bottom right, I can select on the left side here one of the filter criteria. And for example, I'm interested in a publication type. I would like to see, for example, publications which are review articles. So what I'm doing here is I'm looking to a range of approximately 2 years, a year and a half, and I'm getting more than 200, 300 review articles. So what is interesting here is that I can go into these specific publications. So I can look at the abstract, I can see links appearing. So these dots you see are links from this specific concept to other types of data. There is a possibility to do further filtering. If you have a local installation of the system, on the public version we don't allow to do that, but if you have a local installation of the system, you can download this data, you can use the API, etc. And one of the things which are very important here is you can follow links. So the combination of 300 articles here is linked to all these different data types. That's, in a sense, what we do with the platform. If you look from a little bit more high-level perspective, we cover for the moment more than 140 different data sources. A number of them are relevant in the demo of today, data sources related to genes, proteins, etc. If you look to all these data sources, we try to keep them up to date as good as possible. And if you all combine them together, you will see this information here popping up as this is the graph and every source is contributing. So for example, if I'm taking some gene-related data sources, you see here that NCBI gene is covering one part of the graph. If I'm taking, for example, UniProt, for example, is taking another part of the graph. And so every source is combining information together so that you can get what you want. Okay, this is in a nutshell Discover. I'm going back to the presentation. And so let's briefly explain the data sources I would like to take into account. So this is a demo. I'm trying to create some, let's say, mock-up data sets that I could use, but which are relevant, which are not just completely out of the blue. So for this demo, I took the cosmic genes, and from the cosmic genes, if you are familiar with cancer research, you probably know cosmic as a database. Cosmic genes, and in cosmic you have a list of curated genes. You could say these are very relevant cancer-related genes, well-described, well-known cancer genes. So I'm looking for a target maybe outside this list of cancer genes. It could be a strategy that I say, okay, I would like to come up with a target which is maybe not known by default as a well-known cancer gene. So I will try to see if I can exclude from this list some information. I'm interested here in colon cancer for today's demo, so I took a certain colon, a colorectal cancer database. This is a list of approximately 2,000 genes, which are with a certain difference in relevance, relevant to colorectal cancer. So I took this as a list that I would like to compare with, and then I did a little bit of research, and that's my third list. I selected some genes, which I called my experiment, some genes which are upregulated or downregulated in a certain setting. In this case, it was related to prostate cancer because I saw that there was some overlap in other publications that certain prostate cancers are related to colon cancer or to familial colon cancers. So my theory is maybe some of these genes could have an overlap with the previous list, and maybe that could be relevant. That's my search strategy. I would like to start from these 39 genes and see if I can find something relevant. So I'm going here to our test setup of Discover. So what is the difference with what I just showed you before? This is a local installation of Discover. So this means this is something under full control of what I'm doing. This could mimic what you are doing inside an organization. And so you see one small difference in the first appearance is that you have a new data type. I call it gene list. You can call it whatever you want. So this is my collection of genes. This could be the result of your target identification or target validation workflow, different strategies. You could generate different gene lists. You could make a sequence of related data types. You could also manage your samples. I haven't done this here. You can do different things, also define experiments. This is all possible, but I'm just showing you here with a small set of gene lists. So if I click on data, And now what you see here is a distinction between in-house data sources and public data sources, because in this setup, I activated what we call data federation. So I'm linking my local data with all the public data we have here. The public data is dynamically linked and it's unidirectional. My data is not leaking away to the public space. The data is only staying here in this environment. So if I click, for example, on my known cancer genes, you will see that I made a very brief explanation. The date is, of modification is not filled in, so that's just a default date. But I see that I have in my known cancer genes 239 genes and also a gene list of 239. So that means that my known cancer genes, the cosmic genes, are a list of 239. If I look to my colorectal cancer genes, this is a more extensive list. This is a list of approximately 2,000 relevant genes. And then my own gene expression experiment is 39 genes. How do I integrate all this data? I would like to briefly touch on that. Before I can do a search, before I can see here all this data linked together and linked with other stuff, I first need to integrate the data. So let me briefly show you some information about our data ingestion engine. So I'm a data scientist, so I can see this advanced menu. If I click here on data ingestion engine, we have a default hello world pipeline, which is just the default pipeline to showcase how the system works. But I have my webinar target identification and validation pipeline. And this is a very simplistic pipeline to show you how we can integrate different sources. So what is happening? I'm defining 3 different sources, and you see like a workflow of how this data is integrated and finally published in Discover. The steps, I won't go too much into detail in all of these steps, but some of the steps are, for example, synchronizing with a federated class. What does it mean? It means that my data is linked to our public system so that there is a kind of synchronization possible. So to see, is there any identifier in my cosmic gene list matching with the identifiers that you find in the public space? Same thing for these other two sources. They also haven't synchronized with federation. And then you see here some other components which are specifically made for importing CSV files. We have other ones for JSON files, XML files, other kinds of formats to extract the information, to define URIs, which means unique resource identifiers. So unique identifiers, which are the cornerstone of the system, because this is all linked data in a network. So you need well-defined identifiers and then making links. And then you also add labels, proper labels, so you can rename certain things. You can override the names of certain genes, for example, if you want. This is all minimal information that you need to add. Our system is much more extensive. If I click here on this plus sign, you will see that we have a big long list of different components which all have their different powers to execute in the pipeline. So what is happening here is you build a pipeline, you can run this pipeline, you get a report if you run the pipeline. So this is the control here. I can check here. There is a QC possibility here to do an extensive QC. But most interesting here is that you can rerun this on frequent occasions. You can automatically set this, that you can add different data sources. You can define different data sources, you can add different data files, you can work with a whole system where you have on the input side a whole machinery of devices which are exporting data. And even, and that's something we can briefly touch on during the demo, the next part of the demo is, there is even a possibility that some outcome from the front-end application from your searching could be re-ingested as input here in the data system, so that you have a turnaround of your data, so that you are searching for a certain information in the front-end application, the search application, and that you ingest this back again. So let's go into what we are aiming for here. I'm starting with my gene lists because this is where I'm starting, and my idea is I see a long list of more than 2,000 genes, and I see here the distribution of my of my different genes. So I can select show me all downregulated genes. It's a small list. Show me all upregulated genes. It's only showing you the possibility for one data set. You can combine different data sets. You can add different filter properties. We only have 2 for the moment. But let me show you, for example, what I'm looking for with my data sources. I would like to see, is there a certain overlap with my data sources? So can I see from all the data sources, where are the genes which are in more than one data source? So if I make a link here, you can quickly do a filter and say, okay, show me the genes which are in my known cancer gene list or my known colorectal cancer gene list. There is an overlap of approximately 140. So this is a very easy way to navigate through the data, to very quickly look into this. But I wanted to do something different. I wanted to say, okay, I'm looking for a bar chart where I make a very specific selection. I would like to see in your gene expression data set, because these are the genes of interest, filter for them and look now if there are any genes which are known in my in my colorectal cancer genes. So they have to be at the intersection. It's an AND clause. And so I find 4 genes which are relevant in my gene list. I can save this search now. So this is like a first filtering. You can add steps. You can save this list, or you can move and say, okay, go into the details and go to the different links and now follow, for example, a link to pathways. So a possibility here is we have some specific components which are not working in this setting. I can go into different pathways. So I see here my genes are linked to different pathways. I can go into very specific pathways, for example, homeostasis. I can make selections. So I can look into the details. What do we know about these genes? What is known in literature? And I can select certain pathways. I can see what are other molecules related to this. What is also very important is that we can showcase nicely what are the different data sources which are in this visualization of data available, or which are providing data. So if you're interested only in reactome, you can very specifically filter for that. If you say, okay, I would only like to see certain links, like this Janet, you will see almost no data anymore, only related links. This is a possibility you have to add different levels of details. So going back from my pathways, I have my genes, I have my pathways. Let me, for example, make a selection. If I, for example, look for an associated disease, colon, and you will see different types of annotations of curated genes. So you could select here certain genes which are, certain pathways which are associated with certain diseases. Again, a possibility to filter and to follow up. Next step could be that I'm going back to my gene list and I'm going into the literature. Or if you assume, that's just if you assume that you found something, so you have your list of genes here, you could, for example, enter a search and could also mimic the same thing. So let's say that you have found something, you can easily do the same thing here as I'm just adding the terms. So what you see here is, oh, I needed OR statements. This is not working. You could just mimic the same thing and then see what is happening here. So what is interesting here is same strategy. Instead of if I'm doing my search and I'm doing a drill down, I can go into all of this, doing my filtering specifically if I'm having a list. And I can go here into my genes and, for example, say, okay, if I'm entering a list of genes, I see Homo sapiens related genes. Just wait a little. And I find here different genes which are in my result list. What is now the advantage? If I click on a single gene, I get all the data we have in the public space. I can do a lookup here. I see different sources adding information. I can have different identifiers to link to that. I have links to other resources to go deeper into this, so I can use this as a lookup system to gain additional knowledge. Or I can follow, again, links and say, okay, I would like to see, for example, are there any key opinion leaders in this domain? And I remove this filter and say, okay, I would like to see, for example, some key opinion leaders who are publishing review articles. And then you can see if some of these authors are of specific interest for you. You also see combining the mesh terms, so the different annotations of the publications, if that could help you in further drilling down in these publications to find relevant literature. By doing an additional search, you see here on the left side that I made like 2 different blocks of searches belonging together. This is the first block, and if I click on this link, you will see the search path you have made. So we started with a gene list. We went to genes and we followed 2 pathways, if you remember well. And here I started with entering a number of search terms. I went to genes, I went to publications, and I'm subsequently able to follow additional links. So what is possible here is, if I'm going back to what we've done before here, is selecting and filtering is very easy. You can set this up as a workflow to say, okay, if you start with your first internal lists of genes, you would like to make specific selections. We made some filterings. You can make combinations. You can follow the links here to the related genes, and from there on, you are in the public space. If you add additional sources, you have a possibility, for example, internal data, to merge this, to compare this with other data sets. If you have a complete workflow, which is a combination of different data types, you can set this up and follow this as a path and share this with colleagues. So this is all shareable. So if I'm selecting here, if I'm following here this link, you can share this dashboard with a colleague. You can annotate the dashboard. So this is, in a nutshell, the basic navigation you can do with a combination of internal data you produce yourself, and public data, in order to set up a workflow that you can make subsequent selections or filtering steps to come down to a list of relevant targets. I'm briefly touched here only genes. You can enter variants, proteins, or other data types, and then come up with a sub-selection which you would like to push further in your workflow. So I will refer back to the presentation, and I would like to stop here and ask if there are any questions at this moment that you would like to ask. So use your virtual raise your hand virtually, and then Marit will help you further. Any questions so far?
There is one question. No, not a question, just a thank you in the chat.
Okay. But if there are any questions, things that I touched too fast, things which are not informative enough, please interrupt and we go.
Yeah, there is one question. How can I use APIs for ontology relationships?
Maybe if you would like to raise your voice, you can also do that to further explain this. But so the question is, how can I use APIs for ontology relationships and for focused searching? So I think you mean you would like to really exploit the relationships between different data types. So, for example, follow the links of your personal gene list to genes and maybe subsequently to pathways, etc., etc. What you see with the front end can be done with the API. So we have an API which allows you to search quite broadly in the system and to retrieve intermediate results. And you can do this, for example, via scripting in Python. And so this can help you to, instead of using the front end, using a script to automatically walk through a system, walk to a sequence of steps you would like to take.
Martin, is this an answer to your question?
Oh, can you hear me?
Yes, we can.
Oh, okay. Yeah, so I have a very focused question, about the ontologies that I use. I think it's very interesting that you have all the different data resources in there, things like literature, but also Campbell databases. So I'm thinking really about APIs for ontological relationships. Can you use APIs and come in with output for like a pre-analyzed search that you already did, that I've already done, for example, with PubMed? Let's say I have a machine learning approach that I've been able to apply offline without ONTOFORCE, but where I've done searches for very specific relationships of genes and drugs and genes and diseases, and then made a network from that, and something comes out of that network, and I have a very focused question. Now, what I want to do is use an API and go through the ontological relationships with an experimental in-house data set, and I want to combine that with those particular input searches. And then you get like a fairly, detailed search with APIs, where you have gene lists from experimental data sets and machine learning output from some type of literature, machine learning literature and NLP approach. But
Yeah.
that's really what I want to combine, because if you just look at literature search based on genes, there's not really the relationship in there that I want. What I want to kind of filter for a network analysis based on NLP, combine that with Campbell, then combine that with in-house experimental data, for example.
Yeah.
So quickly you go into a lot of API searches and queries, right? How is there a complete API access allowed to the ONTOFORCE backend ontologies?
Yes, it is. And you sketch like a situation where you say, okay, you are producing a lot of additional data on top of public data sources. You are performing NLP, you are making a network analysis. That kind of data could be, let's say, well structured and harmonized on the platform. So that means that you can integrate the output of that in Discover as your own data. And then you can also use the API to query that. So it could be a dynamic system running with the different approaches you have, where you are doing, for example, machine learning and more extensive advanced processing of your data, and that you would like to, let's say, link it or touch it or intersect it with the data which is already in Discover. So Discover can be used as a system that you can query, that you can store specific links, relationships between the different data types, genes, proteins, pathways, etc., and that you can consult this.
Right, so that's very interesting. And also another question I have is about specific disease indications. For example, because obviously there's a lot of backend data that's available for cancer, but let's say you're particularly interested in autoimmune disease, then is there a way to figure out just by taking a fair amount of download through the APIs with querying of the ontologies, and then seeing how deeply is autoimmune disorder covered in the ontologies, and are there ways of taking a measure from that, like quantitatively make a statement that ontologies are deeply represented for cancer, but now I want to know it for autoimmune disease, and say how relative to cancer, how deeply is the ontology represented for autoimmune diseases?
Right. Maybe to answer on that, the problem we are facing is that the question you are asking is a question that you can repeat like 1,000 times for 1,000 different diseases. So we are not claiming that we are complete, but you can definitely look into it if you start searching for autoimmune disease and can see, for example, the ontology of all the diseases which fall under that more general term. So you can look into SNOMED or other disease classifications and say, okay, what is the assembly of diseases that you can call an autoimmune disease, and then see what is related to that. What I can say is that we have a coverage, if you would like to make associations between certain diseases and certain targets, genes, etc., that we are covering, for example, open targets, that we are covering a number of other data sources. But it's not that we are covering, let's say, everything in a certain disease domain at this moment. There are still specific initiatives, specific data sources, sometimes very tailor-made for a specific disease area in the public data. I'm here talking about the public data, but it doesn't impede you for doing this yourself. We have a lot of customers who are having this approach. They have a lot of data sources at their disposal, public or private or licensed data. We bring it together for them, or they do it themselves, and then they have a more complete data set to query, for example, related to autoimmune diseases.
Are there automated ontology builders that can be used from within the system? Is the structure similar to SNOMED?
It's similar to SNOMED, but we also cover MedDRA, we cover ICD-10, we cover MESH, we cover the human disease ontology. So it's quite broad, but there is at this moment, no automatic ontology builder.
Okay.
It's more like exploiting the existing ontologies. It's like being able to link to it, being able to follow, let's say, parent and child's relationships, etc.
Okay. Yeah. Thank you. Very interesting.
Thank you for your question, Martin.
Thanks for the question.
I see another question from Andrew. Is there a way to follow a specific relationship between entities of data types?
Yes, I haven't demonstrated that to you. I can, if you want, quickly go into that and briefly show you. It's maybe easier to demonstrate that. So, just going back to my public version of Discover, you see here TP53 and number of publications. If I'm going back to what I was previously searching, I'm sorry, and I see more links. You see here some links, for example, to in between publications. So you see here links from publications to other publications. These publications are citing other publications or are cited by these publications. That's, for example, what we call a typed relation from one group of entities to another group of entities publications. If I'm going back in my search, and let's say that I'm taking colon cancer just for the sake of showing this, and I'm going to clinical studies, and I'm selecting, for example, just American clinical studies to have a little bit smaller data set, what you see here is a link, for example, just a second, to for example, active substances. Clinical trials are related to active substances. No, there is no specification here. But if I'm showing you organization, we have like show for clinical trials the participating facility, the lead sponsor, etc. I can do the same thing for proteins, for genes, for variants and genes, variants, diseases, etc. So that's is that enough of an answer, Andrew? Okay. Next question. I think can we run Sparkle queries? I think that's the next question. So that's somebody is familiar with Sparkle and RDF. So no, the system, the platform doesn't support Sparkle queries. So it's all semantics underneath, and what I have shown you in the pipelining is using RDF, but it's not possible at the moment to execute Sparkle queries.
Okay.
And
there is also a question from Wolfgang. Can you link from another application or maybe a document into Discover Gene using an URL?
Yes.
Philip?
Yes. So there is a possibility to use permanent URLs. So it means that you can create a permanent URL by the construction of your prefix as the name of the application. So if I'm going back here, the name of your application, for example, this is discover.com, and you can link very specifically to one concept by using, if I'm taking here now a certain clinical trial, by using the URI. So there is a possibility to construct a URL which can have a direct link, a direct landing page in Discover on a specific concept. And this could be done with an Entrez Gene ID or a human genome nomenclature ID. This is possible.
Okay. He has a second question. And could a user construct this URL?
Yes, if you just explain a little bit how to do it, it's not very difficult. So it's I'm maybe taking the risk of trying to do it myself. So it's just something like this. If I'm typing, you can all follow my screen, I think. And I think if I'm doing this, should work. No, but it's something like that. It's quite easy. It's just like a construction, but it's something like permanent URL, and it's in a similar kind of approach. I can't say it by heart.
Okay, thank you.
Other questions?
I see one question, and it is: are the public sources live? Or in other words, is the UniProt public endpoint used, or is the data loaded into Discover?
Yeah, good question. It's a very fundamental thing on our platform. We have chosen not to work with direct federation of all these public data sources. And why? Because you see a very, let's say, neat and flexible way of doing filtering, where we combine sometimes 10 different data sources in one dashboard. So that means that you are depending on the weakest link. So we do not have, let's say, a live link, live federation link with all the public data sources. In place, what we have is that we have a very well synchronized workflow. So this pipelining that I quickly showed you is applied to all these 146 different data sources. And that makes it very, let's say, well manageable to bring all this data together and to manage the linking. But indeed, this is something to discuss about, because for some applications that could be a challenge, but we are continuously working on improving that. So this is quite successful up to now. So is that enough of an answer for the person asking this question?
Yes, the person, the name, I'm sorry, is hidden, so I cannot direct his name. Let me see.
Okay.
Yes, it's clear. Okay, thank you very much.
Other questions so far?
I don't see any new questions in the chat or new raised hands. So if, yes, there's one more in the chat. The question is, can you jump from a set of matches to a new set via property?
Via property.
Yeah.
So I think you mean like if you have a list of genes, for example, or a list of proteins, can you jump to another set or make direct overlaps? Not if you do not load this as a data source. This is a feature which will come in the next version of Discover, so that you're able to load lists of genes and that you can compare lists of genes amongst each other, compare it with the existing data. I think that's a question going in that direction. So this is a feature that will come.
other final questions? No, I don't see them coming for now, but if there are any questions, please feel free to reach out to us and we can discuss this offline. But for today, thank you all for attending this month's webinar. Philip, thank you for presenting, and we wish you all a pleasant day. Thank you very much.